Well, hi there. Lunch bell. It would appear that sea lunch is starting. So today in our Algebra 2 notes, we're focused on quadratics. Specifically, we're going to complete the square. And our essential question is, how do I solve a quadratic equation by completing the square? And I know what you're thinking. What on earth is completing the square, Mr. Kingsbury? Well, in order to explain that, I need to go back a little bit, because ultimately what we're going to do here is we're going to use kind of a cool situation to help us solve. So let me see if I can explain. Back in Algebra 1, you first started your study of quadratic equations, specifically quadratic trinomials, but quadratic equations in general. And you should have looked at how to graph them and their characteristics, and at one point should have started talking about factoring them. See, a quadratic equation is the result of multiplying two polynomials. It could be a monomial and a binomial, but usually it's a binomial and a binomial. You're multiplying two things with two terms. And for the most part, quadratics they're kind of messy. A lot of times they can't be factored. You have to use the quadratic formula, which we talked about last time. However, there are a couple of unique cases where the factoring is very interesting and it follows a pattern. One of those is called the difference of two squares. We're not going to look at that one, but it has a very unique pattern, which once mathematicians figured out the pattern, they figured out how to use that pattern to factor very quickly. The other one is called the perfect square trinomial. Now, you know, when we square something, that means we're multiplying it by itself. Well, the perfect square trinomial is the result of multiplying a binomial by itself. And the result, and I won't show you all the pieces, but the result is this. If I multiply a plus b times a plus b, I get a squared plus 2ab plus b squared. Or if I multiply a minus b times a minus b, I get a squared minus 2ab plus b squared. And what's interesting is this can be written as that binomial squared. And this is really what interests mathematicians. See, anytime you can get something with an exponent, you can take a root to get rid of that exponent. So as mathematicians started to investigate ways to solve quadratic equations that looked like this or even worse, they realized that if they could get their equation in this form, where there's a perfect square at the beginning, a perfect square at the end, and then the middle was the result of taking the square root of both of these things, multiplying them and multiplying it by 2, if they could get this perfect square trinomial form going on, they could go from a trinomial to a binomial squared. And then they could simply take the square root of both sides, since it would be equal to a number, and that would then give them the ability to solve. So they started working on ways to make their quadratics into perfect square trinomials. And that's what we're going to do today. We're going to take a quadratic equation that is not a perfect square trinomial, and we're going to use a little algebraic manipulation, and we're going to turn it into one, primarily so that we can get this form and then turn it into this form. Then, once we have this, we can solve by square rooting and adding or subtracting, and then we have our answer, which is awesome. So yeah, we are going to we're going to do that. So let me see if I can show you. There are a lot of other skills in here. I mean, I could spend time talking about how do you complete the square and getting into all of that. It's not a difficult thing. Let me show you just an example. I got a couple here pulled up. So for example, if I had r squared minus 6r, I need to know what I would add here to make this into a perfect square trinomial. Well, if you look at the middle, regardless of whether it's adding or subtracting, the middle is 2 times the square root of the first term times the square root of the second term. So I'm looking at this. That means this term has to have the square root of our first term and the square root of the term we're looking for in it, and we multiplied it by 2. Well, the square root of r squared is r. So if I get rid of this r, what that means is that negative 6 is the result of multiplying the square root of this term by 2. So I could work it backwards. I could take negative 6, divide it by 2, and square it. That would be negative 3 squared, which is 9. So that would be completing the square. It's not a huge, difficult task. But if you'll notice, I now have a perfect square, r squared, as the beginning of my first term. I have a perfect square, 9, as my last term. The square root of r squared is r. The square root of 9 is 3. And if I multiply r times 3, I get 3r times 2 is 6r, and that gives me this. So it's a perfect square trinomial. Well, what I'm going to do is use this idea with a quadratic that already exists. You know what? Let me show you another one, just so you have the general feel for what this is. Let's do one that's addition. How about we do a squared plus 12a plus something. So again, I take this middle number 12, I divide it by 2, and I square it. So that's 6 squared, which is 36. And again, perfect square, perfect square. If I take the square root of each of these, that's a times 6. And if I multiply 6a times 2, I get 12a. So it's a perfect square trinomial. That means that it factors to the square root of the first term plus the square root of the second term squared like that. This one up here would be r minus 3. Square root of r squared is r, square root of 9 is 3, and you always use that sign right there. So that's what I'm going to do. I'm going to use this concept to complete the square, and then use the fact that this particular type of quadratic has a very special way to factor that I can use in my favor. I'm going to use that, and we're going to solve. So let me just throw one up here, and we'll go from there. All right, here we go. Let's start with, let's work with the simple and work head to the sublime. So let me start with something like this. A squared plus 14a minus 51 equals 0. Please note, 51 is not a perfect square. Also, it's negative. Whenever we complete the square, we will always end up with a positive here. Always. So the first thing I would do is add 51 to both sides, because I don't need that. What I need is the first term and the middle term. Certainly the middle term already has an a, which is the square root of a squared. I just need to figure out what the last term would be, what I need to add here to make this a perfect square. And again, like I did with these examples, the easiest way to do that is to take 14 and divide it by 2 and square. So that's 7 squared, which is 49. So I will add 49 to both sides. On the left, I get a squared plus 14a plus 49. Please note, I can't actually add the 49 to 14a or 1a squared. They are not like terms. On the right side, though, I could definitely add 51 and 49. That's 100. Well, that's beautiful. That's exactly what I want, because now I can factor this. The square root of a squared is a. The square root of 49 is 7. And I will use this sign, the sign of the linear term, which is positive. So I get a plus 7 squared equals 100. And to undo a square, we take the square root. So if I take the square root of a plus 7 squared, then I have to take the square root of 100. Now this is where things get a little interesting. On the left, the square root and the second power, or the square, they cancel. And I'm left with a plus 7. On the right side, I take the square root of 100. And I know a lot of you right now are going, Kingsbury, it's just 10, no big deal. You're half right. The square root of 100 is 10. It's also negative 10. And if you don't believe me, multiply negative 10 and negative 10. You will still get positive 100. So this is where we have an interesting thing happen. because we have a plus 7 equals plus or minus 10, and we can't really solve those together, so we'll split them up. Either a plus 7 equals 10, or a plus 7 equals negative 10. Now, in both cases, I'm going to subtract 7. And I get a equals 3. And over here, I'll subtract 7. I get a equals negative 17. And unlike absolute value, where we did this before, you don't have to check these. They are both correct, I promise. That's completing the square. In fact, that's solving something by completing the square. And it's kind of a neat thing. There are some that are a little more difficult. You'll notice that ours is already equal to 0. That helped. Let me do a couple more so that you can see this in its entirety. And I will do one that has a much more complex linear coefficient, just because I want you to be able to see that and understand how to deal with it. I don't know that we will actually ever need something like that or work on something like that in class. But hey, you never know. So let me find one. This is the problem with using other people's stuff. You guys don't know this, but I'm looking at a worksheet right now, which is, awesome. Let's try something with some bigger numbers. We just did that, did we not? I definitely want a negative in there. Oh, no, we did that one. Here, let's do this. All right, so let's do x squared minus 12x plus 24 equals negative 13. I think that's right. No, positive 13. Like that. Now, once again, this is not a perfect square trinomial. 24 is not a perfect square. So we need to get rid of that. I will subtract that from both sides. X squared minus 12x will equal negative 11. Now we figure out what we've got to add to both sides. So I will take the negative 12, I will divide it by 2, and I will square it. Negative 12 divided by 2 is negative 6. Negative 6 squared is 36. And some of you may be going, oh, but Mr. Kingsbury, I plugged in negative 6 squared into my calculator and I got negative 36. If that's the case, then you did not put parentheses around the negative 6 first before squaring. And the calculator is very particular about PEMDAS. If you don't put the parentheses, the only thing it squares is the 6, and then it makes the answer negative. So be very, very, very careful. So I'm going to add 36 to both sides, and that means then I can factor. So I get x minus 6. The square root of x squared is x. The square root of 36 is 6. That's going to be squared, and it's going to equal whatever negative 11 plus 36 is. I think that's 25. Look at that. And then we can square root both sides. So we get x minus 6 equals plus or minus 5. This is where I have to split it up. So either x minus 6 equals 5 or x minus 6 equals negative 5. And if I add 6 to both sides, I get x. That was awesome. X equals 11. If I add 6 here, I get x equals 1. And those are my two answers. So yeah, I wanted you to see one where there was a number other than 0 on the opposite side of everything else. Okay, let me do one more, and then we'll call it a day. We will do more practice in school and class, of course. Let me get you one with a center that's a little bit uckier. Maybe. Oh, I was hoping to find one that would be, I guess, gross in the middle, but I'm not seeing one here, unfortunately. That's a bummer. Well, it is what it is. I wanted you guys to see what happened when you took something, took a linear coefficient and divided it by 2, but it's not going to happen. So let me just find one. Let me find one that ends up being a little more interesting. Excuse me. Let's do this one. This will be our last one. V squared minus 6v equals negative 91. Isn't that nice of them? They already put the constant on the right side, so we don't have to worry about that over here. We just got to figure out what to add to both sides. So I'm going to take negative 6 over 2, and I'm going to square it. That's going to be negative 3 squared, which is 9. So I will add 9 to both sides. I get v squared minus 6v plus 9 equals negative 82, I believe. Fair enough. And then we factor. So the square root of v squared is v. The square root of 9 is 3. We use minus. So v minus 3 squared equals negative 82. So now we split it up. V minus 3 equals... Oh, wait a minute. I skipped a step. My bad. We should square root both sides. Then we'll split it up. So then we have v minus 3 equals, wait a minute, equals the positive square root of negative 82, or v minus 3 equals the negative square root of 82. Whew, those are not fun. Not fun at all. Yeah. So on this side, I will add 3, but doesn't help a whole lot. That means I get v on the left, which is great, equals. On the right, I can't add these. This is a negative number under the radical. That's not a real number. The only thing I can do for the negative 82 is I can remember that when I take the square root of a negative number, I just put I after it. But the 3's just kind of hang out there. This ends up being 3 plus I times the square root of 82. That gets rid of the negative, but that's all I can do. And then over here, if I add 3 to both sides, I got a similar situation. So again, that's 0, and that gives me v equals. Then over here, I got 3 minus I times the square root of 82. I guess we could do a decimal if you wanted, but this is much, much, much more accurate. At any rate, we'll do more in class and talk about them, and hopefully it will be fabulous. I'll catch you later.